So far, we have discussed the Shockley-Queisser limit to the maximal conversion efficiency of a single junction solar cell. However, to derive the Shockley-Queisser limit, we used a number of assumptions that hold for an ideal solar cell. In reality, there are always additional losses in solar cells that we, engineers, try to overcome to get as close as possible to the maximal efficiency. We will explore these losses in this video. The purpose of this video is to present all the additional losses together and to understand how to overcome them. Let's start by recapping the additional optical losses. You see an example of a crystalline silicon solar cell in this slide. The metal grid placed on the front side of the solar cell as the electrode is not transparent to the incident light. Thus, the area under the grid is shaded. The active area, where light can penetrate into the solar cell, is reduced due to this shading. The second optical loss results from front-side reflection. Third, not all the light that enters the solar cell will be absorbed in the absorber layer, because part of it is absorbed by supporting layers. This is called parasitic absorption. Lastly, there are transmission losses. The metal front electrode is opaque to the incident light, so the area that is covered by the front electrode decreases the active area of a solar cell. We can denote the total area of a solar cell as ATOT, and the cell area that is not covered by the electrode as AF. We define the active area coverage factor CF using the ratio of AF to ATOT. Different patterns of front electrodes are used to overcome the shading loss. There has been a lot of work to minimize the metallization at the front of the solar cell. This is a schematic figure of a standard silicon solar cell with an emphasis on the front metal electrode. The front metal pattern is made up of thicker bus bars used to make connections with adjacent cells and thinner fingers. This cell uses 2 bus bars and numerous figures. As discussed in the previous section, the design of the bus bars and density of the fingers is a trade-off between the contact resistance and shading loss. This can be seen if we look at R, the resistance of a metal. It is proportional to the length of the given metal finger and inversely proportional to the cross-sectional area. So you can see if we reduce our cross-sectional area, we minimize shading losses, but we increase resistance. There is a trade-off between minimizing the shading and resistance losses. The trade-off between shading and electrical losses is shown here. If we increase the spacing between fingers in a solar cell, this means there will be a larger active area. This results in lower shadow losses. However, it increases the resistance between the contact electrode and emitter, since the carriers have to travel, on average, a larger distance in the emitter to reach the contacts. Hence, to achieve the minimum power losses, an optimal spacing distance should be determined. A similar relation is present with the finger width. From the right figure, we conclude that the larger finger width is, the higher the shading losses, but the lower the resistances. An optimum finger width exists, at which the power losses are minimal. This illustrates one of the many trade-offs that engineers have to work with when designing a good functioning solar cell. One way designers are getting around this issue is to use interdigitated back-contacted solar cells, or IBC solar cells. In these cells, there is absolutely no front shading from metallization, since there is no metal grid at the front of the solar cell. You may ask, how do they collect the carriers? Well, they actually have two different contacts at the back, one for hole collection and one for electron collection. These contacts are interdigitated so that carrier transport to these contacts is minimal. This is a very advanced concept, and we will be explained it further in the next course, Photovoltaic Technologies. When the light arrives at any interfaces, part of light will be transmitted and part of it will be reflected due to the different refractive indices of materials that form interfaces. Therefore, when a silicon solar cell is illuminated, a part of the incident light is reflected. We can find out how big is the fraction of incident light that is reflected. From the silicon-air interface, we use the Fresnel equations and refractive indices of air and silicon. We easily find out that at the wavelength of 500 nanometers, more than 30% of incident light is reflected from the solar cell. Reflection losses can be overcome by adding an anti-reflective coating. Reflection can be further reduced by adding front texturing. You should remember, however, that there is a trade-off with front surface texturing. When you do this, you essentially add surface area to the solar cell, which increases the surface recombination. However, excellent passivation techniques essentially minimize this effect, so texturing is still a very worthwhile method for reducing front reflection. You can learn more about passivation techniques in the next course on PV technologies. Not all the light entering a solar cell can be absorbed. The light that passes through a solar cell without being absorbed causes the transmission losses. The transmission loss depends on two factors: the absorption coefficient and the optical path length through a material. In the figure, the absorption coefficient of 4 different semiconductor materials is plotted as a function of wavelength. The transmittance of an absorber layer can be estimated by the Lambert-Beer law, which describes the attenuation of the intensity of an electromagnetic wave as it travels through a certain medium. For crystalline silicon material, the absorption coefficient at wavelength of 400 nanometer is 10 to the power of 5 per centimeter, while the absorption coefficient at 800 nanometers drops down to 10 to the power of 3 per centimeter. In a 1 micrometer thick crystalline silicon, without any light enhancement techniques, blue light can be fully absorbed while 90% of red light passes through crystalline silicon solar cell without being absorbed. Therefore, to absorb as much light as possible, light management techniques and appropriate absorber layer thickness must be adopted. Apart from additional optical losses, which generally affect the current density of a solar cells also suffer from additional electrical losses. These electrical losses affect the voltage and fill factor of the cell. Let's take a look at how the fill factor can be affected. The resistances of bulk semiconductor material, metal electrodes, and contact between semiconductor and metal result in the series resistance in a solar cell. On the right, the effect of the series resistance on the JV curve and the fill factor is shown. The JV curve of an ideal solar cell is represented by the blue curve in the figure. The larger the series resistance, the less steep the slope at the open circuit voltage, and the smaller the maximum power point. Hence, the series resistance should be as small as possible to have a high fill factor. The other type of resistance in a solar cell is the shunt resistance, or sometimes called parallel resistance. The shunt resistance is the result of a macroscopic defects in a solar cell which offer an alternative low resistance path for the generated photocurrent. The effects of the shunt resistance on the JV curve and fill factor is illustrated on the figure. The JV curve of an ideal solar cell is represented by the purple curve in the figure. The shunt resistance in an ideal solar cell is infinite, so that there is not any leakage of photocurrent. If the shunt resistance is reduced, we see the slope at the short circuit current density becomes steeper, and the maximum power point is reduced. The smaller the shunt resistance, the smaller fill factor will be. Now let's take a look at factors that influence the open circuit voltage of the solar cell. To utilize solar energy as electricity, we need to separate and collect photogenerated electrons and holes. As we already discussed, recombination process can destroy or annihilate the photogenerated carriers before we separate them. Therefore, recombination strongly affects the performance of solar cells. Solar engineer does his best to minimize recombination of photogenerated charge carriers in the bulk of the absorber and at the interfaces of a solar cell. The bulk recombination is in general the contribution of 3 different recombination processes: radiative, Shockley hole, and Auger recombination. We also need to take into account surface recombination. The lifetime of minority carriers related to the surface recombination is denoted as tau s and depends on the surface recombination velocity. We can sum up contributions of all recombination processes in a solar cell and obtain an effective minority carrier lifetime, tau. The figure presents the efficiency of a solar cell as a function of bulk minority carrier lifetime and the surface recombination velocity. The highest efficiency is obtained at a high bulk minority carrier lifetime and low surface recombination velocity. We can see that when the surface recombination is high, the efficiency of a solar cell is almost independent of the bulk minority carrier lifetime. Therefore, good passivation techniques are necessary to reduce the surface recombination velocity and to increase the efficiency. So for obtaining a high efficiency solar cell, a high quality absorber material and extremely good passivation of surfaces is required. To summarize, we presented that in a practical solar cell there are losses due to shading, total reflection from different interfaces, parasitic absorption and transmission, drop in fill factor connected to the series and shunt resistances, and collection losses because of the bulk and surface recombination. In the next video, we will derive the mathematical expression for the conversion efficiency of a practical solar cell by including all optical and electrical losses.